settle with this for this year, unfortunately. What I'd like to do today is tell you about a series of works over the past 2 years with a bunch of collaborators at UBC, including Mark and David, Wyatt, Moshe, Peter, Chris, and Siobhan, as well as Alex, who I think is in the audience there and not at UBC. And since one of the topics of this conference is low dimensional gravity, one of the sort of interesting applications of low dimensional gravity in the past couple of years is when we take a low dimensional gravitational system and couple it to some auxiliary system. And particularly interesting and maybe tractable examples of these gravitational systems coupled to some auxiliary system is when the auxiliary system itself is also a gravitational system. In these cases, our low dimensional gravitational system we can think of as some gravitating brane embedded in some higher dimensional gravity theory. But these types of theories are not as well understood, and the ADS-CFT dictionary for them is not as sharp as the one that we have for just CFTs. And so these series of papers are all attempts that I have done to try to better understand the dictionary for these gravitating branes and to sharpen it, to bring it to the sort of same level of rigor as ADS-CFT and try to understand what the landscape of these solutions look like. So with some motivation, I'd like to go back to the sort of older question of when a CFT has a good gravitational, a good bulk dual. That is when our CFT correlator is well described by some semi-classical gravitational effective field theory that is something that's weakly coupled Einstein gravity. There's an oldish conjecture that is, the conditions you need are sort of rather simple, or at least simple to write down, that there's a set of necessary and sufficient conditions. These are one, that you need to have sort of large C factorization in your theory. So that is, some 4-point function should factorize into a product of 2-point functions plus higher, plus connected contributions that are suppressed at order 1/C. And this is meant to be the dual of the perturbative effective field theory in the bulk. There's also meant to be sort of a single trace gap or some sparseness condition on the spectrum. So that is, if I looked at the spectrum of the CFT, for low operator dimensions, I should just have the single trace operators that are dual to these perturbative fields in the bulk, and they're sort of multi-trace composites. So these are the low energy gravitational fields. And then up here at order C, I'm meant to have black hole states. And possibly in between, I can have some other things above some gap in the spectrum where things become sort of more messy and non-local. And this is sort of meant to be where stringy type stuff can live in my theory. And the evidence for this conjecture is generally followed from 2 approaches. One of these approaches has used entanglement and quantum information. And the prototypical example of this is this old work of Tom Hartman, who used agreement with the Ryu-Takanagi formula in the bulk to constrain the CFT. So one can look in a 2D CFT and look at entanglement entropies that are not universal, that are not fixed for all theories. And so a simple example is just the entanglement entropy of 2 intervals, an interval A and interval B. In the gravitational theory, we can calculate this entropy using Ryu-Takanagi, and we know that it's just the sum of 2 minimal surfaces, either say this set of minimal surfaces or this minimal surface. And so one can try to ask what one has to do to the CFT in order to find the same answer in the CFT as one gets in gravity. So one finds is that in order to do that, you need certain constraints on the density of states of the CFT. So this is sort of similar to the types of ideas in the sort of the second of those 2 conditions for having a good bulk dual, that there needs to be certain sparseness constraints on the spectrum. Another large class of works use a conformal bootstrap, and one sort of early example of this is the work of Heemskerk et al. There you're counting perturbative about mean field solutions to the crossing equations, and you compare them to the counting of the types of local Bolt interactions you would write down in the field theory. So that is, I find solutions to crossing, and I match them to terms I would write down in my bulk effective field theory. And one finds there's an exact agreement in counting between the CFT solutions and the bulk interactions. This line of work has also been much related follow-up work, making these types of ideas sharper, as well as sort of a huge collection of large end bootstrap tests, understanding, say, not just the effective field theory and the gravitational background, but also understanding how the gravitational theory itself is constrained to look like Einstein gravity plus small corrections. So much of this past work that's sharpening the ADS-CFT dictionary really focused on local properties, that is local fields. But we also know that conformal field theories have many non-local deformations, including defects and boundaries. So for example, I can take two different CFTs and try to join them together. And at the interface of these two CFTs, there's some defect. Or I could even try to take a CFT and join it together along some interface to a theory that's completely gapped out, in which case I sort of have a CFT on one side, and in the infrared, I have nothing on the other side. So I have formed a boundary. This is what one calls a boundary conformal field theory. And this is going to be the main focus of my talk today, these boundary conformal field theories. So the question is, what does the bulk picture look like when we insert a boundary in our conformal field theory? When the CFT has a good bulk dual, it was conjectured by Takanagi that a Bcft is dual to a geometry that has some end-of-the-world brane. So when I draw the bulk dual of the CFT and its boundary, I meant to imagine that in the bulk, there's some end-of-the-world brane extending. And so just as the boundary caps off the CFT geometry, the end-of-the-world brane caps off the dual bulk geometry. We actually know that this proposal isn't the complete story. We do have sort of top-down microscopic constructions of the bulk or holographic dictionary for boundary conformal field theories. And there you can show that the higher dimensional geometry actually caps off smoothly without a brane. And so rather than this picture, it's a sort of a little more complicated, but in addition to the sort of one emergent holographic direction, there's actually some internal compact space. And as we go deeper into this compact space, so deeper into the bulk, this compact space can kind of shrink and contract down to zero. And when the compact space collapses, then the end of the geometry caps off smoothly. So the big question that I want to ask today is, when does a Bcft have a description in terms of semi-classical bulk gravity and possibly some localized gravitating brane or just some other bulk geometry? And the answer might fall somewhere on a continuum. We might think that one possible answer is that if a CFT has a good bulk dual, that any associated Bcft has a good bulk dual. So it's sufficient just to make sure that your original CFT was holographic. Or perhaps an answer is that if a CFT has a good bulk dual, maybe some or many of the associated Bcfts have good bulk duals, or maybe there's very sparse. So even if a CFT has a good bulk dual, it could be the case that almost no associated Bcfts have a good bulk dual. Even when the CFT is holographic, the insertion of a boundary generally destroys that holographic geometry. Why would we care about knowing which of these answers is correct? Well, there's many good reasons, but here are a few I like. The first one is the one I alluded to on my title slide, and that's sort of Euclidean wormholes and islands, that we can think of this brane as some gravitational system that's coupled to an external system, which is our ambient CFT. And then in addition to, say, the disconnected solutions we would find if we only had one boundary, we find connected sort of geometries that link different boundaries together. And these are nice examples or models of Euclidean wormholes. There's also another nice application of thinking about the sort of gravitational system that lives on this brane, and that's that we can at times have a localized gravity on a brane that has an FRW spacetime. So we can find nice cosmological models embedded within ADS-CFT. This is really just sort of turning that other diagram I had sideways and cutting it in half, and then involving in Lorentzian time to find some cosmological spacetime that lives on the brane. A third nice example is understanding black hole microstates. So in sort of the same picture of these cosmological spacetimes, it's often the case that this gravitational brane lives behind the horizon of a black hole. And then we can think of the states of these branes as really sort of generating microstates of the black hole. And the last question is just to ask, how much does a gravitational system have to look like string theory? So we have supposedly all of these large Cfts that have good gravitational or semi-classical Einstein duals, but if we looked up high in their spectrum, would it really look stringy? And one way to ask that is to ask, do these theories have a good spectrum of well-behaved branes? So the types of boundaries we're going to look at in a sense are very fundamental, that they can't be written as a sum of other boundaries. They're sort of, the fundamental building blocks of branes and these CFTs. And so we want to know, do these fundamental building blocks have a nice gravitational description, or are they very sort of non-local, that they can't even be described in some nice sort of stringy way? So I'm going to talk about 3 approaches to answering the question. The first, like I mentioned, for CFTs, it uses entanglement. So we can repeat an analogous computation that Hartman did for 2D Bcfts. In this case, we just look at a single interval in a 2D Bcft. While you needed 2 intervals to get a non-universal answer in a 2D CFT, in a 2D Bcft, a single interval is non-universal. And there is, again, a phase transition in the entanglement entropy. That is, one possible solution for the entanglement entropy in interval is given by this, sort of similar, it's a connected one that's similar to the one you would got without a brane. And there's also a disconnected solution where the RT surface terminates at the end, at the infrared end of the geometry. And so what we'll find is that there's agreement with the gravitational phase transition between these 2 different RT surfaces, as long as we place certain sparseness constraints on the spectrum of the Bcft. These do not seem to be required in universal. It's required in general. And so the Bcfts that satisfy these conditions are not universal. We have to kind of look at a subset of all the possible Bcfts to find the ones that have this property. We'll also take a quick look at some explicit constructions. We'll look for gravitational theories where we understand what the boundary states are. We can find their bulk duals and study their property. So if we tried to do this in a generic large N CFT, we don't have any explicit constructions of the boundary states. There are cases of special CFTs, for example, 4D n equals 4 super Yang mills coupled to some 3D superconformal boundary, where we can find explicit boundary states. And we also have top-down constructions of their geometric dual. I'm not going to talk about these today, but there's some very interesting work that was done on these recently by Van Ramstonk and Waddell. You could try and hope that Virasoro might help you and think about just the generic 2D large CCFT. But again, we don't really know enough, and we have no explicit construction of the boundary states there. But there is kind of one example where we can do things, and that's a symmetric orbifold CFT. That is, we take a 2D CFT and take the tensor product of some large number of them and then quotient out by the permutation group. These are just gravitational enough to be interesting. They're similar to gravitational, like good gravitational theories in many ways, although not true gravitational theories, but they're also just tractable enough to be able to compute things. And so we can write down a large class of admittedly a little bit special boundary states in these theories and try to understand, use that as some hint of what might be typical more generally about large C holographic CFTs. And what we find is kind of mixed, that depending on the seed theory, that is which CFT we take the tensor product of, typical boundary states are sometimes consistent with the bulk geometry and sometimes inconsistent. And so the evidence that these give us is a little bit mixed. And the last approach is sort of similar to the original Bootstrap one I mentioned to you in the beginning. So we can set out to replicate the work of HPPS and their successors for a Bcft. Interestingly here, there's already non-trivial constraints, not sort of perturbatively, but at leading order. And we'll find that these constraints follow from thinking about the causal structure of the bulk theory. That is, what happens when we send signals into the boundary, into the bulk theory, and bounce them off a brane or bounce them off the infrared geometry and see the type of singularity structure they create in the theory when they return to the boundary. These will be relevant whenever the Bcft has a good bulk dual, not just the naive end of the world brane proposal of Takanagi. And actually it becomes sort of a BC analog of the types of things that appeared in an older paper by Maldacena et al. Titled Looking for a Bulk Point. So what we'll find at leading order, the causal structure of the bulk places, again, very restrictive constraints on the Bcft spectrum. And so the space of good boundary conditions for a holographic CFT appears to be very sparse. And so we'll suggest that a Bcft almost never has a good bulk dual, and probably especially almost never has good gravitating branes. So that's my introduction. So let me tell you where we'll go in the rest of the talk. So first, I'll give a review of Bcfts to give you just a quick overview of some of the technology and terms that I'll be using. And then I'll go through these three approaches. So first, talk a little bit about Bcft entanglement entropy at large central charge, then a little bit about large and symmetric orbifolds, and finally, looking at this causal structure of these Bcfts in the bulk, which I'll call looking for and not finding a bulk brane. So let me pause for a moment now to see if there's any questions about what I said and where we're going.
Yeah, Jamie, I did have maybe that's just my misunderstanding, but wasn't there also an example recently that Martinek proposed of an explicit construction of such branes?
Yeah, so there are cases where in the symmetric orbifold theories where we understand what the bulk dual is. So I'm going to talk much more generally, say not about particular theories or in particular boundary states where we can construct a bulk dual, but try to understand whether in general for the typical boundary state a bulk dual exists.
Right, but in some sense you're saying that this example falls into some of the examples that you've already constructed. Is that what you're saying?
Yes.
I didn't see it on the list. You had this list of things. I wasn't sure if this category of examples was actually mentioned.
Yes, yeah. So when we talk about large and symmetric orbifolds, the type of boundary states that people have found bulk duals for are some of the ones that I'll be talking about. There'll be particular examples of those.
Okay.
Any other questions?
No, please go ahead.
Okay. So let's go through a kind of lightning review of boundary conformal field theory. So to define a CFT on a half space, for example, say the upper half plane or half of a sphere, so some disk, we have to choose boundary conditions at the edge to define that theory. And in the infrared, when we flow down to the infrared, we expect these boundary conditions to flow to some set of conformally invariant boundary conditions. And each one of these infrared conformal boundary conditions defines a boundary conformal field theory. In terms of the symmetries of these theories, they preserve some SOD1 embedded in the SOD plus 1 of the theory of the full CFT. It's important to note is that this subgroup of the symmetry that's preserved is not just the symmetry that lives on the brane, but it's some subgroup of the full higher dimensional symmetry. So for example, the dilation operator that you have in your theory is not the dilation operator that just dilates along this boundary brane. It's the one that dilates you along the brane and into the bulk. Because you have such a dilation operator, we also have a new state operator map in a Bcft that we can take states that live here on this hemisphere in the bulk, and we can dilate them or we can contract them back down to a point on the boundary. And so this gives us a state operator map between states on these hemispheres and boundary operators that live on the boundary of the theory. And so we can perform, just like we have the regular CFT operator product expansion, we have a boundary operator expansion, where we take a bulk operator and we expand it as an infinite sum of operators that live at some point on the boundary. Correlation functions in a Bcft are just slightly different than correlation functions in a CFT. One way that they differ is that scalar operators can have non-vanishing one-point functions. So here, a scalar function can have a rather constrained VEV. It's just given by its distance to the boundary and some constant. Bulk two-point functions are no longer fixed by kinematics like they are in a CFT. We can actually write them up to some unknown function of some cross ratio. And both of these, this one-point function and this two-point function, are examples of sort of a kinematic doubling trick. That if we want to sort of understand the kinematics of a Bcft correlator, we can imagine taking our Bcft and doubling it and inserting operators on the other side of the boundary, sort of as if it were a mirror. And so we see when we do this that the 1-point function in the Bcft really does behave a lot like a 2-point function in the Cft, and a 2-point function in the Bcft behaves a lot like a 4-point function in a Cft. These aren't dynamical statements. You can't, calculate them. So you can't say calculate a 4-point function by just doubling, but they do, what they do is sort of determine the correct kinematics. We'll sometimes find it convenient to work with 2 different cross ratios. So one cross ratio Xi and one cross ratio eta. The Xi go to 0 limit and the eta go to 1 limit are just the limit when 2 operators in the bulk become very close to each other. And the Xi goes to infinity or eta goes to 0 limit is just the limit when operators approach the boundary of the CFT. We can, with our boundary operator expansion and our bulk OPE, we can write down boundary bootstrap equations. That is, we can expand a bulk 2-point function either using this regular OPE or the BOE, and equating the two gives us a bootstrap equations we can solve. So here we have in the bulk channel, we have bulk blocks. We take these 2 operators close and expand them in bulk operators. In the boundary channel, we have these boundary blocks, which sum up the contributions when we do the boundary OPE twice. And here is the statement just of the crossing equation, equating the sum of these bulk blocks and the sum of these boundary blocks. When our Bcft is holographic, or we believe it should be holographic, we can write down the most general solution of the symmetries. It has this form. So here there is some ADSD factor, some ADSD foliation of the bulk geometry. And here there are some sort of radial and internal directions. And so this most general metric is some sort of unknown radial warp factor and some unknown internal geometry foliated over over which the ADSD slices are foliated. The important thing to note about this metric is just that there's no unique vacuum. So while a CFT up to the internal space has some unique, the unique vacuum is ADS space, here we have some unknown warp factor, some unknown radial direction that we can't determine. So if we get away with these internal dimensions, then the metric just takes this form. And this is the type of geometry that has some end of the world brane. So we have our ADSD slices, and then we go and we follow this radial direction until the geometry terminates. And if there's no smooth internal directions to end it, then it has to cap off on some brane. When this radial function is just cosh square root of mu, this geometry here is just some piece of empty ADS. And we have some end of the world brane that just terminates this piece of empty ADS. As always, in 2 dimensions, Bcfts behave a little differently than d greater than 2. So in 2 dimensions, we have the notion of a boundary state. So we can view the boundary condition as being prepared by some state on the CFT living in a circle. And these boundary states have some set of constraints. That is, they're annihilated by certain combinations of the Virasoro generators. There's also a nice concept of boundary entropy in 2 dimensions. So one important characteristic of these boundary states that we care about are the overlap of the boundary state with a vacuum. So if we call G the overlap of the boundary state with a vacuum, and we take the log of G, we reach something that's called the boundary entropy. It's a boundary entropy because it determines sort of corrections to the asymptotic density of states in the Bcft. It's interesting to us because in the simplest 2D bulk dual, if we assume the vacuum is ADS everywhere and we have some constant tension brane, then this constant tension brane will sit at some particular radial coordinate, and this tension in the radial coordinate at which it sits can be determined in terms of this boundary entropy. So there's a very simple relation that just says the boundary entropy is given by the arctangent of that tension. That is, it's very directly related to the maximal depth of this geometry. Okay, so that was a very quick lightning overview of ADS Bcft. Any questions about that? Okay, great. So let me talk about the first of these works, trying to understand the sort of landscape of these solutions. So Bcft entanglement entropy at large central charge. So doing the Hartman calculation, but doing it for a boundary conformal field theory. So what is the entanglement entropy of an interval in a 2D holographic Bcft? So it's the usual RT formula like a normal CFT, except the RT surface can end on the boundary brane. So we had these two solutions. There's a connected solution that's much like the solution without the end of the world brane. And we have this disconnected solution where the RT surfaces end on the brane. For an arbitrary Bcft, this connected area in this first one will depend on the radial warp factor. And so it's difficult to compute. It's some non-universal quantity. But the second one is actually much easier to compute. It's universal. It depends only on sort of how deep this brane is in the geometry. That is, it depends only on the boundary central charge or the tension of this brane. The answer at leading order will be universal in both phases if we assume our Bcft has a bulk dual that's just a wedge of ADS plus a constant tension brane. So if this geometry is just ADS, then we know what the solution is. It's the solution the universal solution we would have found in empty ADS. So that's the assumption we're going to make. We can assume that our gravitational theory is given by empty ADS plus some constant tension brane. And then we know what the solutions we're trying to compute are. So in these simple cases, the connected solution, as I just said, is just the entanglement entropy in a regular CFT. And the disconnected phase is almost the entanglement entropy in a regular CFT, except it contains this correction of the boundary entropy, which is just sort of telling you how much geometry has been cut out or added by this brane. And so the actual entanglement entropy then in the holographic calculation is just the minimum of these two possible solutions. So we can attempt to reproduce this bulk calculation directly in the Bcft. To do that, you can use the replica method. So you can calculate the entanglement entropy as the limit as n goes to 1 of the log of trace rho to the n. And so we calculate this taking then these connected partition functions, these replicated partition functions. And we'll calculate these in terms of twist operators in this Bcft. An important difference from a conformal field theory is that a twist operator does not need to be paired with some anti-twist operator. So we can insert a single twist operator. And because sort of, if you want to understand why in terms of the doubling trick, inserting a single twist operator is kind of like having inserted a second twist operator mirrored across the boundary. And so this twist operator has some expectation value. And the easy way to compute it is like this. We think of this twist operator as having cut the geometry and also inserted sort of a second boundary, some sort of epsilon distance away from the insertion point of that twist operator. And so when we take this picture and we glue n copies of them together, what we really get is just some annulus. And so this is an easy computation to do, especially in the limit that this little circle we've cut out of our geometry or the twist operator inserted gets very small. Then this annulus partition function is just dominated by the exchange of the vacuum between the two boundaries. So that's what one finds, that the expectation value of a twist operator in a Bcft is just given by the overlap of the vacuum with each of these boundary states, and then the sort of kinematic factor of the exchange of the vacuum between the two boundary states. So in the limit, pardon?
Sorry, a question?
Yeah.
So normally in a CFT, when we have both the twist and the anti-twist operators, it ensures certain monodromy conditions when you pass across the branch cut. So here, do those monodromy conditions are implemented in some fashion by boundary conditions?
Yeah, so the monodromy here, is really taking you from one copy to the other, but you don't need a second one. As in the statement really is that normally, you want a branch cut. The branch cut has to start somewhere and end somewhere if you're just on a sphere. But here, the branch cut can end on the boundary itself.
Okay.
Sorry, Jamie, follow-up question. I know we've discussed this before, but you can remind me. Does that mean that the boundary state this twist operator lives in the Zn orbifold theory?
Mm-hmm.
So does that mean that the boundary state in the Zn orbifold theory has a component in the twisted sector?
Yeah, that's a very good observation. I think that's something, people haven't recognized, but, as you know, and we've thought about, when you write down boundary states in orbifold theories, you often have the only consistent boundary state often has a sum over different twisted sectors as well. And so here implicitly, when you write this boundary state here in the original theory, you have to lift it to some particular boundary state in the orbifold theory. And that lifted state has twisted sectors included with it.
Great. Awesome.
Yeah, sorry, I'm trying to kind of give an overview of a bunch of different results. And so I'm kind of glossing over a lot of details, but definitely if there's any details that interest you, please do stop me and I'm happy to discuss them. So in the limit eta goes to 0 or eta goes to 1, these twist operator 2-point functions are then easy to calculate. You just take the leading identity term in either the OP or BOE channel. Then the limit eta goes to 0, that's our BOE channel. And so we replace this 2-point function just by the product of these 1-point functions. And the limit eta goes to 1 in the bulk channel, we just replace them by their Cft universal 2-point function. And if we just use these leading terms, we find agreement with the holographic result, that it computes the holographic entanglement entropy we wrote down on the previous slide. So the less trivial part, that all came at once by accident. The less trivial part is to understand when this holds sharply for all eta. So not just in the limit eta goes to 0 or eta goes to 1, but really for all possible eta in a sharp phase transition between the two different RT surfaces. So the full expression of this 2-point function really is a sum over some large number of Virasoro conformal blocks. And we want sort of everything else in these sums in either channel not to matter, that only one term in each channel matters in the appropriate limit or in the appropriate phase. So the answer we want follows from the same type of reasoning, the same type of principle as it did in Hartmann's original work in 2D CFTs, that is vacuum block dominance. So the contribution of all the heavy operators and additional light operators are suppressed for all eta in some channel. And so we only need this leading vacuum term, this sort of identity contribution in either channel in order to get the right answer. So the resulting constraints and making sure none of these other operators, and not too many operators, that they would dominate over the sort of leading identity block contribution, gives them constraints on the orbifold theory. They give, in particular, constraints on the density and OPE coefficients of this orbifold theory. But we can also relate the constraints on this orbifold data to data in the original base theory, which is the theory we cared about originally. In particular, say for n equals 2 in the 2-twist sector, the BOE coefficients of the orbifold theory are determined in terms of the boundary 2-point function and are universal. They depend just on the dimensions of the boundary operators in the Bcft. And so we can use the principle of vacuum block dominance, that nothing else really matters, to constrain the growth of light operators in the base theory, in the seed theory. So we get some constraint like this. It just says the sum over all the light operators, the exponential of their dimension, has to be less than order e to the c in order to get the holographic answer. And so a large C2D Bcft can be consistent with some ADS end of the world brane geometry, but it has some very strong constraint that it satisfies vacuum block dominance, or in other words, that the boundary density of states grows sufficiently slowly. And neither of these are conditions that are necessarily true about all holographic Bcfts. There are sort of additional constraints we need to put on a theory to agree with this bulk picture. Any questions about that? Okay. let's talk about another example of another pro of these BCFTs that we can try.
Yeah, sorry, Jeremy, I do actually have a question. Maybe it's one, but yeah, I guess the slide before that one.
Yeah.
I mean, wouldn't one and one prime in some sense be naturally coupled anyway? I mean, you know, I mean, you know, the set of conformal compatible boundary conditions is not, you know, is not completely independent of the set of conformal field theories. And so you can just tune whatever boundary density of states you want, or I mean, I'm a little bit confused about that.
Yeah, so the statement is we have, so in order to get a holographic, so you know, to say Hartmann's original calculation, in order to get a holographic CFT, 2D CFT, that agreed with the holographic calculation of entanglement entropy, that we had to put constraints on the growth of states of the CFT itself, the density of states of the CFT. And so not all CFTs necessarily have that, or you know, are consistent with that constraint on the density of states. And so this restricts the set of, say, large CFTs that could have a bulk dual to those that obey that criterion. And so what I'm saying is there's a similar constraint that one has to do in the Bcft. So even if you took a Bcft that agreed with Hartmann's constraint for the CFT spectrum, there's also the spectrum of boundary operators. And that spectrum of boundary operators has to obey an independent constraint.
Yeah, my question is, how independent is that constraint really?
Oh, good. Yeah. So good. That's a tough question. So it's a very interesting question to sort of ask, you know, exactly how, you know, how closely are these related to each other? Yeah, I guess, you know, I can't make a sharp statement about that. I can just say that there is this other constraint. It doesn't seem to be directly related to the constraints we've already placed. But I can't argue, because I don't have explicit examples, or I don't have a very sharp argument that would say that, you know, these are entirely independent. You know, you could still hold out hope possibly that imposing the bulk constraint would, by some mechanism that I don't fully understand, also happen to impose the boundary constraint.
Yeah. Okay, thanks for the answer.
So when we insert a boundary in a CFT, the question that I would like to know the answer to is how much space-time do we sort of eat up? So if a holographic dual exists, then the boundary entropy is some measure of the geodesic distance to the IR end of the bulk, that this, you know, the logarithm of this G function that's overlapped with the vacuum is really meant to be some measure of the sort of maximal distance to the end of that geometry. If, you know, and this is true if there's a brane or there's just some other geometry, that there, you know, Rutakanagi tells us that these two things should be related to each other. So if the boundary entropy is less than 0 in order C, we expect this sort of boundary brane to sort of eat up some of the geometry. And so we have some sort of, you know, narrow acute wedge of the bulk geometry. If this boundary entropy is sort of less than order C in magnitude, then this sort of geometry or this brane just kind of sit right in the middle, sort of be perpendicular. If the boundary entropy is greater than 0 in order C, then we have some sort of, you know, larger opening angle. So it sort of allows you to, the entropy sort of creates more geometry. And if the boundary entropy is sort of, you know, it's larger than order C, then we'd probably say there's not really a good bulk description of that Bcft. We really have no understanding of what that would look like. So one place that we can try to ask this question about how much geometry exists is in the symmetric orbifold CFT at large n. We're not going to worry about whether this Bcft, this particular boundary state, has a good bulk dual, but merely ask, in terms of looking at the tension, how much geometry would exist if it did have a bulk dual. Of course, there's very interesting work by Gabriel et al. And also Martinek, looking at some boundary states where the bulk description is understood. But I'm not going to focus on that today. So to understand just a little bit about the symmetric orbifold, we're going to consider some seed conformal field theory C. And we don't care too much about what C is. So C could have a finite or an infinite number of Virasoro primaries. either is acceptable to us. The symmetric orbifold we get by taking n products, the n-fold tensor product of a CFD, and then quotienting by the permutation group by Sn. So this theory contains all the appropriately symmetrized states from the product theory. So if we took some state, psi I1 tensor blah, 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 psi In, then we would get a state in its orbifold theory just by summing over all the permutations to appropriately symmetrize it. This defines some good state in the orbifold theory, but we also have to add in twisted sectors. So that is, if we had, k copies of our seed theory, we should also have a sector of our theory where these sort of k copies have been linked together into one larger circle instead of radius r of radius kr. And this defines states that live in the twisted sector. So it's just some copy of our seed theory on a much larger circle. Yes, and we can ask, what are boundary states in this orbifold theory? So boundary states in a 2D CFT satisfy some particular condition in the Virasoro algebra that Ln minus L bar minus n has to annihilate the boundary state. In the orbifold theory, the Virasoro generator is just the sum of all the n Virasoro generators of the seed theories. It seems very hard to find all the states that satisfy this condition. I have no idea how to do it. So instead, one can impose more constraints on the boundary state, a more constrained gluing condition, and they're going to reflect not just the Virasoro generators in the orbifold theory, but impose some reflection on the entire symmetry algebra of the theory. So in our orbifold theory, we have Virasoro generators for each of the seed theories, and we're going to impose just the same constraint in each seed theory that we impose in the overall theory. So we're going to impose that Ln minus L bar minus n annihilates the boundary state for any I. So this is a much smaller set of boundary states. This is a much more constrained set. And so there's a warning that we're going to look at things that are typical in this class of boundary states, but they may not be typical of all the boundary states in the theory. We'll hope that they're sort of illustrative of the more general properties, but we can't determine that for sure. So it's easy to guess a class of states that satisfy our gluing condition. If we assume we know all the boundary states in the seed theory, so we have some set of boundary states AI for I1 to NB, where NB here could be finite or infinite. These are the boundary states of the seed theory. Then we can just take a tensor product of these boundary states and appropriately symmetrize them. And we find a boundary state that satisfies all of our constraints in the orbifold theory. But this doesn't quite work. When more than one boundary state is the same, so if the boundary condition, in theory, K is the same as a boundary condition in theory L, or rather two of them are the same. Of course, you can't really, in the orbifold theory, pick out one particular theory or another. But whenever we have these sort of coincidences of boundary conditions, then this symmetry, this permutation symmetry, acts degenerately on the boundary conditions. And so we also have to sum over boundary states in the twisted sector as well. So we'll have to add in a boundary state, say if K and L had the same boundary condition, then we have to put that boundary condition in the twisted sector as well and add that into the sum in some appropriate way. So one can show, and I'm not going to today, that the correct boundary state can be written in this form. Don't worry too much about what that formula is. I'm going to tell you the important things I want you to know about it. It's labeled by some vector n, and this labels a number of copies, ni, of each seed boundary condition. So we have some NB boundary conditions, and each ni tells you for one of them how many of that boundary condition appear. So the sum over these ni's has to equal n, because we have one condition for each of the capital N copies of the theory. And then it's labeled by a second vector r, the components of which are each just some representation of SNI. That is the permutation group of each of these collections of Ni seed states. So in this state, we have some sum over all the twisted sectors that live in each of these groups of seed states that are the same. We have another sum over permutations that just make this whole thing appropriately symmetrized. And these representations appear in sort of some counting way. They sort of tell us how to weight the contribution of each twisted sector. So with this formula for the boundary states, it's actually very easy to calculate just the overlap with the vacuum to get the entropy. And so two simple cases that I can show you are when all the seed states are different. And then the entropy just takes this form. It sort of has one term, it's really just the average of all the seed entropies, which is great because the seed entropies are sort of order 1, and this average has an n in front. So we find there's good order C, order n contribution to the entropy. But it also has a term in front, some combinatorial factor that's n log n. So this is super Planckian and bad. It wouldn't be consistent with having a nice bulk geometry. If all the seed states are the same in some representation R, then this formula also has a nice simple form. And again, let me point out the relevant bits. So we have some piece just n times the entropy of the seed state we've chosen, the seed boundary condition. So this is good. It's the right sort of order C contribution. But again, we have some term here that's super Planckian and not good, that it wouldn't be consistent. And then we have some representation theoretic piece here, whose contribution we don't yet know. It depends on log of the dimension of that representation we chose. So if we want to know what a typical boundary states look like, we need to understand the properties of typical choices of our two vectors, n of how much of each boundary state we have, and r of the representations of these permutation groups. So typical n, there's two cases. If the number of boundary states in the seed theory is infinite, then almost every seed theory will either appear once or 0 times. In fact, almost all of them will appear 0 times, and a few of them will appear 1 time. It'd be very unlikely to have the same one appear more than once. So this is like our case that all the seed states are different that I showed you 2 slides ago. And so there we know in this case that the boundary entropy looks super Planckian and does not have a nice bulk interpretation. When the number of boundary states is finite, then almost every the boundary conditions will all appear more or less the same amount of time, at least at leading order in n. They'll all appear n over the number of boundary conditions nb, with fluctuations that are subleading. And so since they all appear sort of in order n amounts of times, these ones basically work the same as the case when all the seed states are the same. Sort of divided by nb doesn't matter. We might as well just assume all of the boundary states, only one boundary condition appears, so all the boundary conditions are the same, and we just take one of the ni to be n, and that will have the same properties at leading order. In terms of typical representations, of course, when the number of boundary conditions is infinite, because each boundary condition appears sort of at most once with high probability, then all the representations are trivial. But when the number of boundary conditions is finite, we have to ask, what is a typical representation of this permutation group? What is a typical representation of the permutation on n elements? Thankfully, this is something that we know, or rather that mathematicians have worked out for us. So there's a very nice theorem that says that there's positive constants C0 and C1, such that in the limit n goes very large, the measure, that is the number or the probability that the log of this dimension of the representation divided by the square root n factorial is greater than or C0 and less than C1 approaches 1. So there's some concentration of measure where almost surely all the representations have dimension in this bound. So what's very nice though, looking at our formula for the boundary entropy, we see that the contributions we cared about, this sort of combinatorial part that had a n factorial in this dimension, are exactly what appear in this nice math theorem. This is something, I guess, it was kind of nice. Usually math theorems, you have to twist them into the form you want, but here actually in the boundary entropy, we find exactly the same ratio of 2 terms that appear in the theorem. And so this becomes very simple, and it just says that the boundary entropy, if we just subtract away this n times SI term, has to be small, that it's bounded, it's greater than C1 times square root n minus C1 times square root n, and less than minus C naught times square root n. We find that there's then only possibly subleading corrections to this entropy with very, very high probability. And so what we can summarize from our study of permutation orbifolds is that typical boundary states have entropies that scale like order n when the number of boundary conditions is finite, and scale like n log n when the number of boundary conditions is infinite. So in this first case, that a bulk theory that was sort of well modeled by or rather a holographic Bcft that's sort of well modeled by a permutation by this, the symmetric orbifold Cft with a finite number of boundary conditions could be consistent with a macroscopic bulk dual. But if it's sort of better modeled by a permutation orbifold that has an infinite number of boundary conditions in the seed theory, or an infinite number of Virasoro primaries, then it's not well modeled by a bulk dual. That we have super Planckian boundary entropies, and we wouldn't know how to write down a bulk description that's consistent with that. So that's sort of mixed, I'd say mixed evidence for whether or not a good bulk dual exists for these theories. Any questions about that?
You started with very special set of conditions, right?
That's right.
So,
Yeah,
and you're not sure if those are typical or not, right?
that's right. We're sort of looking under the lamppost.
The answer that you're getting, whether it's typical or not.
Yeah, we're really looking under the lamppost. So this is what's typical of the boundary states that satisfy this this nice gluing condition. It's very difficult to know whether or not that really is going to be instructive about all the possible boundary states. So this is sort of something we can calculate and some evidence, but I don't think this is very conclusive. So to continue to the last bit of evidence, that looking for a bulk brane, we take sort of the bootstrap approach. So the bootstrap approach for CFTs begins with a perturbative expansion about the mean field theory, or the generalized free field solution. And that is, we take our 4-point function and we expand it about this disconnected contribution. And this leading order contribution is universal because the product of two 2-point functions is universal in a CFT. The form of the 2-point function is fixed by conformal invariance. And so, this expansion we say is valid because, in other words, the bulk vacuum is also universal. The unique solution is ADS. But we know the Bcft vacuum solution is not universal. And we know that the Bcft 2-point function is not universal, that it's only determined up to some unknown function of a conformal cross ratio. And the bulk picture suggests that very large deformations of this background should be allowed, that we consider very different metrics and very different warp factors. This non-universal piece is going to encode the leading order sort of free propagation on this non-trivial background, so sort of free bulk fields that propagate on this gravitational solution. So before we can do the sort of perturbative analysis like in HPPS, we really need to understand what is the CFT origin of this non-trivial leading order free solution, this free gravity solution. So let's begin by analyzing the simplest bulk model and try to extract some lessons from it. And the simplest bulk model is just taking a wedge of empty ADS that ends on some end of the world brane. This 2-point function that we're going to calculate in this background will come from taking, say, a free scalar field in this background and just solving its field equation. And we can write the solution in terms of some mode expansion, where these psi's are some radial wave functions in this sort of radial direction. And the phi's are free fields that live on these ADSD slices. The masses of these free fields on the ADSD slices are determined in terms of the radial eigenvalue of these radial wave functions. In terms of this expansion of the bulk field, it's actually very easy to read off the boundary conformal field theory data. And that's because the boundary conformal blocks are exactly the same as the propagator, as the bulk 2-point function, the ADS-D bulk-to-bulk 2-point function of these fields that live on our foliated slices. So one can write down a very simple formula then that relates the 2-point function, the Bcft, to some particular limit of these radial wave functions and the conformal blocks using this expansion. What extracts from this calculation very easily are the boundary dimensions. They're computed just in terms of the masses of these ADS-D fields. And the boundary operator expansion coefficients are also determined in terms of the coefficients that appear in the radial wave functions that weight these different ADS-D fields. So we can't solve the bulk equations exactly, but what we can find are the asymptotics. So we can find the asymptotic boundary operator dimensions. These are sort of what one might think of as sort of like the double trace operators in a CFT. And they have some nice regular asymptotic spacing where everyone is separated just by some sort of angle, some angle phi b that's determined in terms of the brane location. It's some angular measure of just how deep this brane lies in the bulk. We also extract the asymptotic scaling of the BOE coefficients, which is also determined in terms of this brane location. And the lesson we learned from looking at this very simple model is that the bulk brane in the Bcft appears very easily in terms of the asymptotic spacing of these boundary operators, as well as their BOE coefficients. So what we'd like to know from that lesson is, what is the CFT meaning of this data and where does it come from? In order to answer that question, we need to think a little bit, not about a Euclidean 2-point function, but a Lorentzian 2-point function. When we look at the Lorentzian 2-point function, one question we can ask is, when do we expect a CFT 2-point function to become singular when we continue to real time? If we think about the CFT itself, we have the sort of regular light cone of our operator extending into the future, but we also, that light cone can bounce off the boundary. So we expect to have singularities both sort of along this light cone here, emanating from where we insert the operator, and then also where that light cone itself bounces off the boundary of the CFT. When we look in the bulk, it gets a little more complicated because we can send signals that bounce not just off the boundary in the CFT, but they can go into the bulk. So we could send a signal into the bulk and it could bounce off the brane at the end of the bulk and return to the boundary. Or it can go into the infrared geometry if there's not a brane and return at some later time. But the time that it returns is not necessarily the same time it would return if it had gone just along the boundary through the CFT itself and hit the boundary of the CFT and come back. So it could come back earlier if this brane is very close to the CFT, that there's not much depth to the bulk geometry, or it could come back sort of later if the bulk CFT is sort of very deep, the radial dimension is very large. So we can directly check this is the case. So we can solve for geodesics that go into the bulk and reflect off the brane, and then plot when these geodesics return to the boundary. And it looks like this. So this is where we insert the operator. Here are the boundaries of our CFT. And these curves are when we get signals that return. The different curves is for some different choice of brane tension, for some different depth of the bulk geometry. One finds is that the geodesics return on some curve of fixed cross ratio. They return some cross ratio that's just determined in terms of this angle, this depth of the bulk brane. So the semi-classical bulk suggests singularities in the 2-point function that are unexpected in the Bcft, that we wouldn't have predicted from the CFT alone. You might ask how to think about these singularities, and the answer is that we should think about them in the same way we think about singularities from bulk interactions in ADS and a holographic CFT, in the way that was described in the Looking for a Bulk Point paper of Maldacena et al. So their bulk interactions can generate new Lorentzian singularities in a CFT 4-point function that are not predicted, say, by the naive Landau diagrams in the CFT itself. They occur at some different cross ratio than you would have expected. And so in the bulk point story, this divergence comes from a sum over an infinite tower of double trace CFT operators whose dimensions are integer spaced. And so the phases under this analytic continuation all align to give you some divergence. Of course, it's not expected to be a true divergence of a CFT correlator. So expect this regular spacing that all aligns coherently to break down at some scale. It breaks down at the scale at which the bulk becomes non-local, that is the gap of the CFT, and then it sort of smooths out from some singularity into a resonance instead. So we can translate this story to a holographic Bcft. We have a semi-classical bulk brane predicts a new singularity in the Bcft, and we see this through the alignment of phases of the asymptotic semi-classical operators that are analytically continued. In the full Bcft calculation, we also expect it just to be a resonance. That is, we expect our brane not to be some infinitely thin object that could exactly reflect this null signal. That we expect this brane to have some thickness, some resolution to it. And so when this singularity breaks down in the Bcft, we're sort of probing the non-local properties of our boundary condition. So we can try to check that this works. We find it useful to work in radial coordinates. So instead of this xi, I can rewrite it in terms of radial coordinate rho. What's nice about this radial coordinate rho is that this whole Lorentzian region we're interested in all lives on the unit circle. So we hit the first singularity at rho equals 1, and we go through this time-like region just as some angle on the unit circle, and we reach this reflected singularity at rho equals -1. So the boundary conformal block in these radial coordinates and at large dimension becomes very simple. It really just goes like rho to the delta. And so when we plug in our formula for the Lorentzian time at which our signal returns, we find that they all align exactly as desired. So when we put in e to the I phi b, this particular angle, this exactly cancels the contribution in the spacing in the operator dimension. And so all of our boundary operators add coherently in the two-point function. And so the moral we extract is that a holographic Bcft has a causal structure encoded in the asymptotic spacing of these double trace operators. We don't expect this to continue indefinitely. It holds up to some gap, the gap that determines when our brane becomes non-local, but nothing fixes this careful alignment in the Bcft as far as we can determine, even when the CFT is holographic. So we found no simple condition that enforces the spacing to hold. And so again, we'd like to say is that just like when we need to assume large N factorization of correlators to have a good bulk CFT, we must assume the relevant mean field theory that determines the gravitational causal structure. And so what we'll then say is that holographic boundary conformal field theories really should be thought of sparse among all the possible boundary conditions for a holographic CFT. Again, sort of very similar to the moral that we found from looking at entanglement entropy. Of course, we can go a little bit beyond this sort of end of the world brane story. You might wonder if it's really just end of the world branes that are precarious. And maybe really they should all have some higher dimensional bulk geometry. So we do have known top-down holographic Bcfts without bulk branes, so we can study them and ask what happens. One example is the ADS2 cap. Well, I see I'm going a little bit over, so maybe let me just skip some of the details. Okay, so we have these solutions. They have some asymptotic ADS3 cross S3 geometry, and they're dual to a 2D Bcft. They happen to have curvature singularities in the IR at the so-called caps of these geometry. And the metric of this solution takes some form of ADS2 cross S2 that's been warped over some Riemann surface. So just to give you a picture of what that looks like, here is the sort of ADS2 foliation of our geometry. Here's where it terminates in the infrared smoothly. There's some S2 at every point here. And then there's this Riemann surface. And on this Riemann surface, the boundary, the CFT, lives here. The radial direction here, as we go into the bulk, is really the sort of radial direction on this upper half plane in the way I've written this Riemann surface. And the caps live here at some points. So we can just consider typical null geodesics in this background that start in the boundary and then go into the space with no momentum on the internal space. So they look like light fields. And then we can just plot what their trajectories look like. And they kind of do things like this. So they go into the infrared geometry and they just continue to hop around in this infrared geometry. In fact, they seem to be sort of attracted towards the caps of this geometry. So the null geodesics get trapped by the IR caps and don't return for at least very long times. So in this particular case of the ADS2 cap, there's no need for operator alignment, at least for generic operators. That's not the only thing that can happen in top-down examples. So another nice class of top-down examples are interface CFTs. These are just like Bcfts. In fact, we can view an interface CFT as a Bcft by folding, that we really think as the two different sides that live on either side of this interface as living on the same side. And they're just, it's a product theory, and these product theories are only coupled at the interface, and you could send signals from one part of the product to another by bouncing them off the interface and getting something back in the other theory. So a nice example where the bulk dual of an interface CFT is known is the supersymmetric Janus solution. So again, let's not worry too much about the details, but just that the metric takes some form of ADS2 cross S2 cross T4, again, warped over some Riemann surface. So these are sort of very similar to the other geometries. And if a null geodesic can go from one side to another in finite boundary time, we expect there to be a singularity, like in our simple brane cases. The nice thing about these supersymmetric Janus solutions is that the two-point function has already been computed holographically for us, so it's not a calculation we had to do. This nice paper of J.Sully et al. And so one finds in the supersymmetric Janus solution that actually you do have a regular asymptotic spacing in the boundary operator dimensions. So there's some parameter kappa, which controls the sort of warping of these ADS2 slices that really determines how far it is to go from one side to the other. And this sets the asymptotic spacing of operator dimensions and determines when you see some singularity from sending a signal that goes from one CFT and bounces and comes back again. So I'd like to just give a refined moral and then a promise that I'll stop, and apologies, I just went a little long. So it seems from both looking at our bulk brane examples and also these higher dimensional top-down examples, there's a spectrum of possibilities for the bulk dual of a holographic CFT that has a boundary. One case is that there's just no infrared geometry, that there's very large non-locality that one sees in the infrared, and that's why the operator dimensions don't align. So there's no sharp singular signal that you get out showing the singularity of reflecting off the geometry. Another case, which is very regular, is some infrared brane, where you hit some very thin object and return at some very well-defined time. And then it seems like in the middle, there's something, maybe it looks a little bit more like a classically chaotic infrared geometry. That one can go into the bulk. There is a good bulk geometry, but one spends a long time there. That one can sort of bounce around, and that a signal doesn't come back at some short time. And so, what I'd like to suggest is that that this very fuzzy no infrared geometry, or some very non-local infrared geometry, is sort of the indicative of there being an irregular boundary spectrum, maybe what would be a typical boundary operator spectrum. And this end of the world brane is a very regular, highly constrained spectrum that's not at all typical or generic. And that in between, there's something maybe in between, something that's also rather sparse and constrained, but we can still have some very complicated spectrum that's describing the sort of complicated, sort of chaotic dynamics in this infrared geometry. So I'd say that things here on the left are much more typical, and things here on the right are much more atypical. Let me just list a few open questions to end. So I think a few questions that I think are very interesting to think about. So one is that it'd be nice to know if there's some connection between the sort of classical chaos one sees in these complicated infrared geometries and some notion of chaos in the boundary spectrum. It'd be nice to understand if those ideas can be related and made sharp. It's also interesting to try to, having understood sort of where the leading order two-point function comes from, to try to repeat the analysis of Heemskerk et al., or the more modern incarnations of that. and match not just this leading order solution, but match the sort of perturbative corrections and crossing to the sort of all the interactions one could write down. Of course, one can't do that in general because we don't have any idea what the space of all these possible leading order solutions is, but one could choose simple examples. For example, empty ADS plus an end of the world brane, and try to see, given that very constrained starting point, can we match the perturbations around that on both sides? And lastly, vacuum block dominance was enough to have a consistent Euclidean picture in 2D, but it'd be nice to understand the sort of Lorentzian picture there as well. So how does one understand, can one show that vacuum block dominance would be enough to fix the causal structure as well? Or are these two separate constraints that one needs to impose in a 2D Bcft? Let me stop there. And apologies for going long.
So, sorry, in the case in which you have like a light ray bouncing off the brane, what kind of reflection condition did you put on the light ray bouncing off?
In terms of, we're just sort of just tracing the geodesic. So when we actually did like the condition, we did like the simple case of empty ADS plus an end of the world brane. We just put a Neumann condition on the field. But you can impose different boundary conditions and you get the same phenomenology. It just slightly shifts things a little bit.
Because geometrically, it seems like when you have like when the tension is positive and you have an angle which opens up, should not return back to the conformal boundary.
Yeah, no. So we were always considering the global case. So it's true. If you're if you have a flat boundary, say so it's a half plane. It's true. If the boundary is greater than if it's whatever the entangled angle is obtuse, that you bounce off it, you go into the bulk. But we're putting a global case, so you always have to come back to the Cft.
I see. Thanks.
So it's just sometimes it's harder to draw pictures with things that are curved. So I might have drawn just straight lines when that was easier.
Maybe one quick question, because people are getting ready for dinner.
In the case where you consider a fuzzy end of the world brane, why would you expect the intersection with the boundary to still be a well-defined defect? It could still have a thickness on the boundary also, right? Then it would not be a true Bcft. It would have something else. It will have a bit of thickness to it.
Can you repeat that? I don't think I quite understood.
Yeah, what I mean is that instead of considering a completely local end of the world brane, if you consider a bit of thickness to it, then why would you expect it to still be, completely thin on the boundary? It could still have a thickness on the boundary. It wouldn't be a true Bcft then, because you have a defect with the thickness.
Oh yeah, I'd say those are different. So if the brane has a thickness in the bulk, that is not going to correspond to fuzzing out the boundary condition in the Bcft, but rather a fuzzing out in the reflected signal. So that would correspond to the size of the gap in the boundary in the Bcft spectrum.
I see. Okay.
Well, we should probably conclude with this, the last talk of the last evening session. So Jamie, thank you very much for this presentation.
Thank you.